The following audiobook contains AI-generated content and may contain errors. MyAudiobooks.ai presents Steel Box Economy: How Containers Rewired Global Trade. The modern economy was quietly rewired by a steel box that most people notice only in passing. The shipping container looks boring by design. Corrugated walls, corner fittings, standardized doors, and a number painted on the side. Yet by changing how cargo is handled, it helped redraw trade routes, port cities, factory networks, labor markets, and security policy. The puzzle is this: the container did not make shirts, electronics, coffee, machinery, or auto parts more valuable. It changed the journey around them. Once that journey became faster, cheaper, and more predictable, the geography of production began to stretch. Before containerization, most general cargo moved as break bulk freight. That meant goods were broken into many separate pieces for transport: sacks of grain, crates of manufactured goods, drums of chemicals, bales of fiber, boxes of parts, rolls of paper, and odd-shaped machinery. Each item had to be counted, lifted, stacked, tied down, recorded, and protected. A ship's hold was less like a modern storage grid and more like a three-dimensional puzzle. Workers packed cargo tightly by hand, using basic lifting gear. Heavy goods went in one place, fragile goods in another, dangerous goods somewhere else. A single voyage could involve many shippers, many destinations, and many kinds of packaging. Every transfer created friction. Cargo moved from a factory or warehouse to a truck, from the truck to a dock, from the dock into a shed, from the shed into the ship. Then the chain repeated in reverse at the other end. At each step, someone touched it, checked it, sorted it, and exposed it to weather, delay, loss, or damage. Ports were built around that labor-intensive rhythm. Ships often waited for berths. Once alongside, they could spend days loading and unloading. A ship made money at sea, but break bulk shipping forced vessels to spend a large share of their working lives tied up in port. The costs were not just wages and dock fees. Uncertainty spread through the entire trading system. If delivery dates were unreliable, firms held larger inventories. If cargo could be damaged or stolen, insurance and packaging costs rose. If paperwork was complicated, clerks, brokers, and customs officials absorbed more time. If schedules varied, factories could not depend on distant suppliers with confidence. Trade is shaped by more than distance on a map. The real barrier is the cost and risk of moving goods from one useful place to another. A country may have a buyer across the ocean, and a factory may have a cheaper supplier abroad, but the relationship becomes fragile if the transport chain is slow, leaky, and unpredictable. So the old system limited the scale of exchange. It favored goods valuable enough to justify the trouble. It rewarded firms that could tolerate delay. It made faraway sourcing possible, but difficult to coordinate. The world traded before containers. It simply traded through a physical system that fought back at every handoff. The practical breakthrough came from Malcolm McLean, an American trucking entrepreneur who understood the frustration of cargo transfers from the trucking side of the business. The frustration was simple: why unload a truck piece by piece at the dock, then reload the same goods into a ship when the load itself could travel as a single unit? Early experiments involved putting truck trailers onto ships. That idea helped prove the concept, but it had a weakness. A full trailer includes wheels, axles, and a chassis that are useful on roads and wasteful at sea. The sharper idea was to separate the freight-carrying box from the road equipment. The container could ride on a truck chassis, be lifted off, stacked on a ship, then placed onto another chassis or rail car at the destination. McLean's Sealand helped turn that idea into regular service rather than a one-off experiment. By the late 1950s and early 1960s, containerized routes were linking North American and Caribbean ports. The innovation was not a box alone. It was a system of ships, terminals, cranes, truck chassis, schedules, and business practices built around the same reusable unit. That distinction matters. A strong metal box is helpful, but a strong metal box in a world of incompatible ships and cranes is just another awkward object. The container became powerful because it could plug into different modes of transport. The same module could move by truck, by ship, and by rail without the goods inside being unpacked. Standardization turned that module into global infrastructure. The International Organization for Standardization, through ISO Standard 668 and related standards for container fittings, helped codify common dimensions, ratings, and connection points. The details sound technical, but they created the common language of the system. A crane spreader could lock onto the corners, a ship's cell guides could hold the box, a rail car could accept it, a truck chassis could carry it, a terminal could stack it. The 20-foot equivalent unit became the basic measure of container capacity. A 20-foot container counts as one 20-foot equivalent unit. A 40-foot container counts as two. This unit lets carriers, ports, analysts, and governments describe capacity and throughput, even when actual boxes vary in length or type. Once many actors invested around the same standard, the system gained momentum. Ports bought cranes, shipping lines ordered container ships, railroads built intermodal terminals, trucking firms bought chassis and tractors, manufacturers redesigned packaging and warehouse flows. Each investment made the others more useful. That is the network effect of standardization. The value of joining rises as more of the network joins. A container, then, is less like a package and more like a promise. It promises that a load prepared in one place can be handled efficiently by strangers far away because they recognize the same geometry, the same locking points, and the same operating logic. The container changed trade by turning cargo into a unit load. A unit load is a group of goods handled as one object. Instead of lifting hundreds or thousands of individual packages, the system lifts the container. The goods inside may be varied and delicate, but the transport network sees one standardized steel unit. That unlocks intermodal transport. Intermodal transport means a shipment moves across different modes, such as truck, ship, and rail, without the freight itself being unpacked at each transfer. The container is the bridge between modes. It makes the journey continuous even when the vehicle changes. Goods are packed at or near a factory. The container is sealed. A truck carries it to a port. A crane lifts it from the truck chassis and places it in a stack or onto a ship. At the destination port, another crane unloads it. The container may move onward by rail to an inland terminal, then by truck to a warehouse or distribution center. Through all of this, the cargo inside remains in the same box. Continuity reduces touches. Fewer touches mean less damage. They also mean fewer opportunities for pilferage because sealed containers are harder to casually open and repack than loose cargo in a shed or ship hold. Storage becomes simpler because boxes stack in predictable patterns. Planning becomes easier because terminals can assign slots, schedule cranes, and move units in sequence. Ship turnaround changes dramatically. A break bulk ship could sit while workers slowly assembled a load inside its holds. A container ship can be worked by specialized cranes that move boxes in repeated cycles. Faster loading and unloading increases the useful life of the vessel because more of its time is spent carrying cargo rather than waiting beside a pier. The gains also move inland. Railroads can run double-stack services where infrastructure allows it. Truckers can haul containers over standardized chassis. Warehouses can receive sealed loads with more predictable timing. Customs and documentation can attach to containerized shipments in more consistent ways, even when the paperwork remains complex. Lower handling costs reduce the unit cost of transport. More reliable schedules reduce the need for buffer inventory. Lower damage rates make distant sourcing less risky. Faster ship turnaround expands effective capacity. With transport less uncertain, firms can split production into more specialized stages. A company can source components from one country, perform assembly in another, ship finished goods to a third, and keep the process coordinated closely enough to be commercially viable. The container does not write the contract, design the product, or manage the factory. It makes the physical movement cheap and reliable enough for those decisions to work at scale. Distance still matters, but it changes character. A supplier across an ocean may become more practical than a supplier nearby if the containerized route is dependable and the total cost is lower. The world does not become frictionless. Instead, the pattern of friction changes. Ports, rail links, road corridors, terminal capacity, customs performance, and schedule reliability begin to matter as much as simple mileage. Containerization is often described as a cause of globalization, and it was, but it was never the only cause. The The same decades also brought tariff reductions, new trade agreements, better telecommunications, changing corporate strategies, improvements in manufacturing technology, and financial systems that made cross-border production easier to organize. The careful claim is stronger than the simple one. Containers lowered the cost and uncertainty of moving many goods, which made global sourcing and export-oriented production more feasible. Other forces created incentives to use that capability. Policy opened doors. Telecommunications helped firms coordinate across distance. Corporate offshoring strategies searched for cost advantages. Manufacturing systems made it easier to divide production into stages. The container made the physical chain more dependable. Evidence on trade growth has to be read with that bundle in mind. Trade expanded in many places after containerization spread, but the box alone did not cause every increase. Its effect depended on ports, roads, railways, customs systems, capital investment, labor arrangements, and the kinds of goods a country produced. Some economies could plug into container networks quickly. Others faced bottlenecks that the box itself could not solve. Port geography shows the change. Containerization favored terminals with deep water, large yards, strong cranes, road access, rail connections, and room to expand. Older waterfronts built for break-bulk cargo often struggled because they lacked space for container stacks and truck flows. New terminals emerged away from traditional city docks, sometimes closer to highways, rail corridors, and industrial land. The system also encouraged hub-and-spoke logistics. In a hub-and-spoke network, large vessels call at major hubs, and smaller ships, trains, or trucks distribute cargo to regional destinations. Transshipment is the transfer of containers from one vessel or route to another along the way. A container may cross an ocean on a large ship, shift through a major hub, then continue on a feeder vessel to a smaller port. This geography creates winners and pressure points. A successful transshipment hub can become a strategic node in global trade. An inland intermodal terminal can pull logistics activity away from the coast and connect factories to seaports hundreds of miles away. Trucking corridors and rail terminals become extensions of the port, even when they sit far inland. Containerization also spread beyond its early centers. As the network reached more regions, its infrastructure and operating logic followed. But connection and development are different outcomes. Export-led strategies can use container networks to help firms reach global buyers, attract manufacturing investment, and move into higher-value activities. Yet containerized growth can also leave countries at the margins if local firms remain stuck in low-value assembly, if ports are efficient but domestic suppliers are weak, or if inland infrastructure fails to connect producers to terminals. The container can open a gate, but it does not guarantee what passes through it. Deep industrial capability depends on skills, institutions, finance, energy, education, supplier networks, and policy choices. A country can have a modern port and still struggle to capture much value if the surrounding economy cannot support complex production. So the geography of the container age is not just coastal. It runs through dry ports, logistics parks, customs zones, rail ramps, truck depots, manufacturing clusters, and border crossings. The shoreline remains important, but the real map is a network of synchronized nodes. The container created enormous efficiencies, but efficiency always redistributes power. Dock labor felt that change directly. Break-bulk ports required large gangs of longshore workers to load and unload cargo by hand. Container terminals needed fewer workers per ton of cargo, but more specialized equipment, planning, maintenance, and coordination. In many ports, unions bargained over the transition. Agreements often involved new work rules, compensation, jurisdiction over container-related tasks, or protections for existing workers. The details varied by country and port, but the broad pattern was clear. Containerization reduced demand for some kinds of manual dock work, while raising demand for crane operators, mechanics, dispatchers, planners, equipment technicians, security staff, and information system roles. The work also moved. Cargo that once passed through urban piers and dockside warehouses shifted to specialized terminals, inland depots, and distribution centers. Some waterfront neighborhoods lost jobs and activity. Other areas gained logistics parks, truck traffic, rail yards, and warehouses. The container did not eliminate labor from trade. It changed where labor was needed, what skills mattered, and who had bargaining power. Automation extends that shift. Automated stacking cranes, remote operations, gate systems, and terminal software can raise throughput and reduce some labor needs. They also require high capital investment and strong technical management. Ports that automate may handle larger volumes with more precision, but they can also face labor conflict, cybersecurity risks, and dependence on complex systems that are hard to fix when they fail. Security policy changed for the same reason the system became efficient. Sealed boxes move through the world in huge numbers. A sealed container reduces theft and damage, but it also makes inspection harder. Opening every box would destroy the speed advantage that makes containerization valuable. Inspecting too few creates security risks. Governments therefore try to manage risk through data, targeting, scanning, trusted shipment programs, and radiation detection. In the years after September 11th, United States policy placed greater emphasis on security for containers loaded abroad and bound for American ports. That included stronger scanning practices, radiation detection systems, and programs designed to identify higher-risk shipments before they reached United States territory. The challenge is ongoing. The same system that enables fast trade also creates a vast inspection problem. The container economy faces another tension: scale. Megaships can lower transport costs per container when they sail full and run efficiently, but they also concentrate risk. When a very large ship arrives, a port must handle a surge of boxes, trucks, rail movements, chassis demand, and warehouse appointments. A bigger ship can save money at sea while creating pressure on land. Congestion reveals the hidden dependencies. A shortage of chassis can trap containers at terminals. A rail delay can fill port yards. A labor dispute can slow an entire gateway. A cyberattack can interrupt bookings, customs filings, or terminal operations. Bad weather can close a port and ripple through schedules worldwide. A disruption in one node can move through the network because the system is tightly connected. Resilience concerns make the trade-off harder to ignore. Firms once treated ultra-lean logistics as an obvious gain. Less inventory, faster movement, lower storage costs. But lean systems leave less slack when transport is disrupted. Some companies now weigh lower costs against redundancy, supplier diversity, inventory buffers, and alternative routes. The container remains central, but the strategy around it is changing. This brings the story back to the original paradox. The shipping container looks simple because the complexity has been pushed into standards, terminals, cranes, vessels, software, contracts, inspection systems, and inland networks. The box is visible. The workflow around it is the deeper invention. The quiet thesis is this: the shipping container changed the economy because it standardized an entire workflow. The world did not just get a better box, it got a common operating system for moving goods. As you keep thinking about the objects around you, ask how many of them were shaped by a journey you never saw. The next time a plain steel container passes by, it is worth remembering that some of the biggest economic changes arrive without looking revolutionary.